All right. Another classic example of phase spaces, or of illustration of how we can use phase spaces, is to think about how a pendulum, how we might represent the behavior of a pendulum. And so that's what we're going to do. But I'm going to take this away because it's distracting. Take that away because it uses up whiteboard space. All right. So let's start with what exactly a pendulum is. We saw one swinging there. But let's give a little reference frame. There's a stick that holds it up. There's a ground that the stick can be on. And a pendulum swings from one side to another along a path like this. And along that path, we can characterize the position as some distance from some zero place to some maximum place. Well, this is going to be minus because over to here. And at any given time, the pendulum is moving at some velocity. So there are two variables that describe the state of this pendulum at any given time. So the state of the pendulum at time t can be characterized, can be characterized by the position at time t and the velocity at time t. So, in this very simple case, there are two parameters that describe the state of the pendulum at any given time. Now, in an ideal world, this behavior is described very simply by some sines and cosines, which we're not going to get into. But in an ideal world, pendulums behave nicely when displacements are small displacement. The mass of this string is zero mass string, I'll just call it, and that there's no friction. All right, that's a very ideal case. We don't get it very often, but it's useful to think about, and it makes all the math very nice and easy. All right, so let's go into a little bit more detail about this swinging. I'm going to do a couple of smaller diagrams. So at the very beginning, let's say, of a swing, the pendulum is out here. So d is equal to the max, and the velocity is equal to 0. So the state at this time is max, 0. All right. Then we let it go. And at this point, this is 1. At time 2, d is equal to 0, and v is equal to velocity max. So that's here. So the state at time 2 is equal to 0, max. And then the pendulum continues up to this point, time 3. uh, which is at D. Actually, this is minus max, isn't it? Careful. So here at time 3, D is equal to plus max. V is equal to 0 again. So the state at time 3 is equal to max, comma, 0. All right, so that's one swing of the pendulum. So then what happens? The pendulum swings back the other way. So we have time 3 here, still this, but then it starts swinging back this way. So at time 4, D is equal to 0, and V is equal to minus max, because it's going the other way, right? It's going the other way, it's going this way. So the state is equal to 0 minus max. And then when we get back to this point, time 5, this is S4, D is equal to minus max, and V is equal to 0 once more. So the state at time 5 is equal to minus max, 0. Back to that state. So now so that's the dynamics, that's how it moves. But now let's draw it in phase space, and I've said that the two state variables are D and V. So we need a graph that has one axis being D and one axis being D and one axis being V. So at time 1, minus max, the D is minus max, velocity is 0, so that's this point here, 1. At time 2, state 2, D is now 0, so D0 is here, and velocity is max, so it's up here. At time 3, D is max, that's 2, and velocity is 0 again. So then that's 3. So now we've got to here. Now we come back the other way. 4, D is 0, and velocity is minus max. So that's here. And then 5 comes back to here. And it turns out if you do some intermediate states, you get a nice thing like that. So an ideal pendulum has an attractor. So this graph of all the states is a continuous line. It's a circle, but it's symmetric, and it comes back to where it goes, and then so you get up here, and then the whole thing starts again. So this is an attractor for an ideal pendulum. Now, in the real world, I can get rid of this now. In real life, pendulums usually have small displacement. If you swing on a swing set, that's small displacement still, barely. Small displacement in real life. In real life, the string has mass. But usually not very much. Usually 0 mass is good enough. But the thing we can't escape in real life is friction. So Perhaps you've seen the Bill Nye experiment where he starts with the bowling ball here on a long string and lets it go, and it goes whoop, and he doesn't move his head, and the bowling ball comes right back and doesn't quite hit him in the head. That's friction, both at the pivot up here and air. All right, so what really happens then, in Bill Nye counts on it the bowling ball not getting back to minus max, to getting back to something a little bit shy of that. And the velocity is 0. Off it goes. Similarly, the velocity when it gets to 0 isn't going to be quite as much as it was before. And it's not going to go quite as far here, and it's not going to be going quite as fast here. So in real life, what happens, I'm missing my marks here, is that. And the equilibrium, the pendulum comes to rest. I shouldn't take my pendulum down, but the pendulum comes to rest at that point when it doesn't displace and velocity 0, right? So in real life, the attractor of a pendulum has this curvy bit, and the nature of this spiral will be determined by a number of things. One of them is friction, one of them is this length, which we've held constant, another one is this mass. No. And those of you, it's primarily going to be, as long as this, we assume that the mass of the string is 0, then this mass doesn't matter. Right. So that's probably a simpler explanation of phase space and attractors than the predator-prey one, because the parameters in the predator-prey one are a bit more difficult to get up here. All right, another example of attractors. I'm going to do one more, and then I'm lagging by about a day, so a homework assignment is coming, but not right now.